Right. So when we talk about Hooke's law, right? So Hooke's law is a law that is applicable on your elastic substances, right? Substances that are able to undergo elastic deformation. Those substances are the one on which we can apply our Hooke's law. So when we go ahead and we talk about elastic substances, we can go ahead and talk about a spring. So a spring is, of course, has the ability to undergo stretching. So if we have a spring and we add a weight to it, the weight will provide a force, and that force will cause the spring to extend. It will cause the spring to become longer. Now, according to Hooke's law, what does Hooke's law state? Hooke's law states that force, the force is the weight, okay? The force and the extension of the spring are directly proportional to each other up till the elastic limit. If you guys have ever played with a spring, you guys would notice that you can pull the spring, right? You can pull the spring, you can apply force on the spring, and what will happen that each time the spring is going to come back to its original value, right? Whatever was the original length of the spring will come back to its original value. That is what you guys would note. Now, there's also another situation, and that is if you really apply a lot of force. If you really apply a huge amount of force on the spring, what will happen? The spring is going to deform. What do I mean by deform? That the spring will not return back to its original shape. It will not return back to its original length. At that point, you can go ahead and you can say that our spring has been permanently deformed. So, up to a certain limit, up to a certain point, whatever weight you will go ahead and apply, the spring will stretch. And the stretching of the spring or the extension of the spring is going to, be directly proportional to your excuse me. It's going to be directly proportional to the force you are applying, right? But when you go ahead and you exceed the elastic limit, what will happen? The spring will not be able to return back to its original length. And since the spring is not going to be able to return back to its original length, you are going to go ahead and you're going to observe that the spring is going to be permanently deformed. So this is basically what your Hooke's law actually is. Now, when we talk about our Hooke's law, we have an equation for it. What is the equation that we have for it? The equation we have for it is F is equal to KE. Where F is the force in newtons, K is something known as spring constant. Spring constant is about the stiffness of the spring, how stiff your spring is, right? Spring constant tells you the stiffness of the spring, and that is basically the stiffness of the spring, that is your spring constant. And then we have the extension. The extension is the increase in original length. Whatever was your original length, let's say it was 5 centimeter. You applied the weight and it became 7 centimeter. So 7 minus 5, our extension is 3 centimeter. So our E is going to stand for extension. That's going to be 3 centimeters. So that's the formula, F is equals to KE. Now, we also have a graph that you guys need to know about. This is the graph for Hooke's law. We have force and we have our extension. Now, the graph for our force and extension, it looks, initially you will observe a straight line. Now, the initial straight line, you will observe a straight line. What is the straight line telling you, right? The straight line is telling you that the force and the extension are directly proportional to each other. How can you tell? Whenever you guys look at a graph, how can you tell that anything are directly proportional? You have a straight line going through the origin. Whenever you have a straight line going through the origin, that means that you are seeing direct proportional relationship. And this relationship will continue until the elastic limit or until the limit of proportionality. That's the term that you should know. After you have crossed the limit of proportionality, your graph is going to start to curve. Why? Because now the spring has been permanently deformed. It is no longer able to come back to its original length. So the proportional relationship will be gone, right? So the point up to which you have see a directly proportional relationship, that is known as our limit of proportionality. And we can go ahead and we can find out the spring constant using our graph. How can we find out the spring constant using our graph? By taking out the gradient. By taking out the gradient of the graph, I can go ahead and I can calculate the spring constant of the graph. So I will take my force, right? And I will take my extension. I will find out the gradient of the straight portion, right? We have to find out the gradient of the straight portion. That is very important. So we are going to go ahead and find out the gradient of the straight portion, and that should tell us the value of K as well, the spring constant. Now, so this is one thing that we have to know related to our topic of, Hooke's law, right? We have to know related to the topic of our deformation. Now, okay, hold on, just give me 1 second. Okay, so now that we have our basics down, let's go ahead and take a look at a few questions related to the topic, and let's actually see how we can study or how we can solve the questions related to it. Okay, the first question says on figure 3.1, draw an extension against load for a spring which obeys Hooke's law. Monami, can you go ahead and annotate on the screen, show what the diagram is going to look like? Good job. State the word used to describe the energy stored in a spring that has been stretched or compressed.
Elastic energy.
Elastic potential energy. Good job. Figure 3.2 shows a model train traveling at speed v approaching a buffer. The train of mass 2.5 kg is stopped by compressing a spring in the buffer. After the train has stopped, the energy stored in the spring is 0.48 joules. Calculate the initial speed v of the train. It's a 4-mark question, so it's slightly tricky. Go ahead, give this a try. See if you guys can figure out how to solve this.
Yes, will it be 0.62?
Good job. It's going to be 0.6. So over here, when you're going to go ahead and you're going to take a look at the question, you have to realize that kinetic energy of the train is turning into elastic potential energy, right? So whatever is the kinetic energy of the train, that is going to be turned into elastic potential energy as the spring is going to be compressed. So when the train is going to reach the spring will be compressed and the kinetic energy will become equal to elastic energy. Our elastic energy is 0.48. So our elastic energy is equals to kinetic energy. So our kinetic energy will also be 0.48. You will write down half mv square and then you will simply solve for velocity, which will come 0.62 meters per second. An athlete of mass 64 grams is bouncing up and down on the trampoline. At one moment, the athlete is stationary on the stretched surface of the trampoline. Figure 3.1 shows the athlete at this moment. State this form of energy stored. What do you think, Monami?
Elastic potential energy.
Good job. The stretched surface of the trampoline begins to contract. The athlete is pushed vertically upwards and she accelerates. At time t, when her upwards velocity is 6 meters per second, she loses contact with the surface. Calculate her kinetic energy.
$1,152.
1100 what? Sorry?
52.
You are using. Yeah, good job. That's fine. Calculate the maximum possible distance she can travel upwards after time t. Anybody get the answer for this? Aryan, Ruda, anyone? Monami, did you get the answer yet?
This is at 1.8 meters.
Good job. You're simply going to do kinetic energy is equals to gravitational potential energy. The kinetic energy calculated was 1152. So that is equals to gravitational potential energy mgh. Your mass is going to be 64 and your gravity is 10. So you will go ahead and calculate the height. That's going to come as 1.8. Good job. In practice, she travels upwards to a slightly smaller distance than the distance you calculated. So in In reality, she's traveling a less distance compared to what you just calculated. Why do you think that is?
So will it be because we did not calculate air resistance?
Yes, because we did not take air resistance into account. State the name of point X. Yeah, Ariane, it would be better if you said limit or proportionality. That's better. Okay. Elastic limit. Actually, when you guys will do A levels, you'll understand the difference. Elastic limit is slightly different compared to it. Say limit or proportionality. State the name of the law that the spring obeys between the origin and the point X. What is the law called, Monami?
Hooke's law.
Good. Figure 3.1 shows part of an extension load graph for a spring. The spring obeys Hooke's law between points A and B. Monami, can you complete the graph, please?
All right, miss.
Good job. State the name of point B.
Limit of proportionality.
Good job. The average value of load between A and B is 6 newtons. Calculate the work done in extending the spring from A to B. Any idea how we're going to go ahead and solve this?
Miss, will it be 4?
Is it going to be 4? Um, Hold on.
Oh, wait. Miss, will it be 36? I think I did a mistake.
No, it's not going to be 4. What did you say, Monami? Sorry?
Will it be 36?
No, it won't be 36. Yes, Ariane, good. 18 joules is correct. 18 joules is fine. Ariane, your answer 18 joules is fine, but I think you need to do a conversion that you've missed.
Zero 0.18.
0.18. Over here, you guys can apply two formulas. Okay. Actually, let's just talk about one. Forget the other one. Work done is equals to force into distance. Fine. The force is 6 newtons. You have to look at the distance. So we know that over here at 12 newtons, the extension is 3 centimeter. So when we will take a look at the load of 6 newtons, so 6 is half of 12. So the extension will be half of 3. So since this is 6, right? This is 6. So 12 divided by 2 is 6. So 3 divided by 2 is 1.5. So you'll multiply it by you can go ahead and you can multiply it by that, but you have to remember that you have to go ahead and you have to I'm sorry, I'm saying 1.5, you don't have to do 1.5, you will take 3 centimeter, right? So you will do 6 multiplied by 3, but before you do that, you have to remember to divide it by 100. Force into distance, the distance is 3, right? The average load, average value is 6 newtons. So 6 multiplied by 3 upon 100, and you will end up getting 0.18. So that's the answer. The spring has an unstretched length of 4 centimeter. An object is hung on the spring and the spring length increases from 4 centimeter to 6 centimeter. Calculate the mass of the object. If you guys need to see the graph, let me know. I'll scroll up.
Can you scroll up to the graph?
Sure.
Should it be 0.80?
0.80 kg. Good job. So what you're going to go ahead and do is that you're going to start by finding out the value of K, because you have to use the formula F is equals to KE, right? So you have to start by finding out your K. So you read from the graph, your force is 12. You have to find the K and your extension is 3. So 12 upon 3 is going to give you 4. 4 Newton upon centimeter. This is your K. Now, the question is basically stating that what is the mass of the object when we have the extension over here. So to find the mass of the object, we first have to find the weight of the object. So the weight of the object will be the force. Our K is 4. Our extension is going to be 6 minus 4 gives us 2, right? So it's going to be 2. So our force is going to be, when you go ahead, you're going to go ahead and do this. 4 multiplied by 2 is equals to 8. The answer you will get is going to be in grams. 1 minute. This answer is going to be 8 newtons. This is going to be force. Then now you have the force, which means you have your weight. So weight is equals to mg, right? So your weight is 8. The mass you have to calculate, g is 10. So 8 divided by 10 will give you 0.8 kilograms. Good job, Munami. The object is immersed in a liquid but remains suspended from the spring. The liquid exerts an upward force on the object and the length of the spring decreases to 5 centimeters. Calculate the upward force exerted on the object by the liquid. Good job, Aryan. Your answer is correct. It will be 4 newtons. So you guys know that the value of K is 4. You guys already calculated in part 1. The extension is going to be, so 6 centimeter was the length. It's going from 6 centimeter to 5 centimeter. So the extension is 1 and we have to calculate the force. So we will do F is equals to KE. So you're going to end up getting F is equals to 4 newtons. Good job, Aryan. That's correct. Okay. Figure 2.1 shows the extension load graph for the spring. Point P is the limit of proportionality. State the name of the law obeyed. We know that this is Hooke's law. Describe two features of the graph that show that the law is obeyed. What are the two features? Good job. One point is that you have a straight line. What's the other point? No, Aryan, that's not the point. The second point is that the line is going through the origin. Those are the two definitions that we have. Any question they ask you guys about, your directly proportional. So to prove that anything is directly proportional, you need to have a straight line that has a constant gradient, and it needs to be going through the origin. Those are the two things needed. Next, they're saying that on figure 2.1, sketch a possible continuation of the graph when the spring is loaded beyond the limit of proportionality. So what do you guys think? How is the graph going to look like once we hit the limit of proportionality? Monami, can you go ahead and annotate the graph for part B?
All right, Miss.
Good job. You will basically see a curve because your spring has been elastically deformed. Okay, state Hooke's law. What is Hooke's law?
Law that states that force applied to a spring is directly proportional to the extension.
Good job. The force is directly proportional to the extension provide up to the limit of proportionality. Okay. Figure 1.1 shows the graph of a stretching force F acting on a spring against extension X on the spring. State features of the graph that show that the spring obeys Hooke's law. We just discussed this. So what do you guys think the points are? We just talked about them.
It's a straight line that passed through the origin.
Good job. It's a straight line that is going to be passing through the origin. Calculate K. This is your graph. You have to calculate K.
$2.5.
Monami, you're missing a step.
Miss, will it be 2,500?
Yes, you have to turn your millimeters into meters. Aryan, you also have to turn your millimeters into meters, right? So when you're going to be taking, for example, your 50, you will have to take it divided by 1,000. So 50 divided by 1,000 you will have to do, and then you will read the force and you will divide the two of them. Next, they're saying the limit of proportionality is reached at an extension of 50 millimeters. Continue figure 1.1 to suggest how the spring behaves when the stretching force is increased to values above 125 newtons. Who wants to go ahead and annotate on the screen how the graph is going to look like? Monami, do you want to go ahead and annotate?
Yes, can you show the question once again?
Yes. Here you go. Give it a read. Let me know whenever you're done.
All right, miss, can you show the graph?
Here you go. Good job. Now also take a look at part 2. Another spring has a smaller value of K. This spring obeys Hooke's law for extensions up to 80 millimeters. On the grid of figure 1.1, draw a possible line of the variation of F with X for this spring. Okay, so Monami, you can go ahead, read the question. Let me know when you're done, and then I'll scroll up and you can annotate and show us what the new graph is going to look like.
Yes, I'm not really sure, but
Okay, Munami, you've done a good job. So you will have a straight line going to the origin up to the 80 millimeter mark. That is perfectly correct. And since they are saying in the question that the value of K is small, so K is the gradient of the line, right? Since K is the gradient of the line, the gradient is going to be smaller because K is smaller, so the gradient will be smaller. So you're going to end up making a line just like this. Good job. Your answer is correct. A spring S is suspended from a clamp, stand in a school lab. Calculate the weight of a 250-gram mass. This is really simple. Can somebody quickly do the questions?
So will it be 2.5 times 10 to the power 6?
2.5 into 10 raised to power of 6. What are you are just, what formula are you using?
F equals FG.
W is equals to mg, that's fine. And what are you doing for your mass? Are you turning it into kilograms?
Yes, miss.
So if you turn that into kilograms, 250 divided by 1000 gives you 0.25. You multiply it by 10, you get 2.5, no?
Yes, miss, I did a mistake. Sorry.
That's what I was thinking. It's supposed to be 2.5. Okay. The student plots a graph of the force F applied to the spring against extension X. At point P on the graph, the line begins to curve. What is the name of point P? What's the name of point P?
Limit of proportionality.
Limit of proportionality. Use the section of the graph where the spring obeys Hooke's law to determine the spring constant of the spring. I'll zoom in on the graph. Good job, Monami. Correct. 45 is the correct answer. Next, they're saying figure 2.2 shows a mass of 0.12 kilogram resting on the bottom of a box. A spring that is identical to S connects the mass in one side of the box. Ignore friction between the mass and the box. The box and the mass are at rest. State the resultant force acting on the mass. What do you guys think? What's the resultant force?
Zero.
0, exactly, because the object is at rest. When they are at rest, the value is going to be 0. The box is firmly attached in a horizontal position to the body of a racing car. As the car accelerates, the spring stretches by 2 centimeter. Use figure 2.1 to determine the tension in the spring. This is figure 2.1. Using this, determine the extension in the, not the extension, determine the tension in the spring.
Miss, can you show the question once again?
Yes, here you go.
Miss, you can go up to the graph. Thank you. Miss, will it be 0.9 newtons?
Yes, good job. So you simply read from the graph at 2 centimeter, the force is 0.9 newtons, so that's the tension. Next, they're saying calculate the acceleration of the mass produced by this tension.
$7.5.
Good job. You will simply do F is equals to ma. You have calculated the tension divided by the mass, and that's going to give you the acceleration. Okay, hold on. Just give me 1 second. An experiment is carried out to measure the extension of a rubber band for different loads. The results are shown below. Which figure is missing from the table? Good job, Munami. It's going to be option B, 17.3. So you will simply 15.2 is the original length. The extension is 2.1. So 15.2 plus 2.1 will give you the new length at 2 newtons. 4 objects are each acted on by only 2 forces as shown. Which object is in equilibrium? Why not B, Monami? Just asking.
Miss, because for an object to stay in equilibrium, there should be no resultant moment.
Yeah, that's fine. When you are going to okay, so there should be no resultant force and there should be no resultant moment. You're right, you're correct. But still, what is wrong with option B? I mean, that's what I'm asking.
Miss,
Because
it's also
over here,
correct, right?
sorry,
It's also correct, right?
option B. No, you can't have two answers, right? They're asking you which object is in equilibrium. So I'm just generally asking that why are you saying specifically D? That's what I was just
Miss,
asking you.
I wasn't sure which one to choose because I think
I'll
both of
tell you
them.
why. I'll tell you why it's not option D. If I look at this arrow, right, forget the other one. If I took look at this arrow, this is the direction in which my object will move, right? This is going to be in clockwise direction, correct, Monami?
Yes, miss.
And if I take a look at my other object, the other arrow, is it not also going to move my object in a clockwise direction?
Ah, right.
So yeah, so it's just going to end up moving in a clockwise direction. That's why it's B and not B. It's not just about don't just assume that because the forces are equal and they're on opposite side, so there must be no resultant moment. Always look at the direction of the arrows and see what kind of movement you're getting. So in this situation, both the forces are producing clockwise movement. Since both the forces are producing clockwise movement, so you're not going to have an equilibrium. The answer is going to be option B. An extension load graph for the spring is shown. The unstretched length of the spring is 17 centimeter. When an object is hung from the spring, the length of the spring is 19.2. What is the weight of the object? Did anybody get the answer yet, Monami?
Miss, is it D?
Yes, good job. You simply have to do 19.2 minus 7, you will get 3 centimeter. You will end up getting 2.2 centimeter. You will read from the graph at 2.2 centimeter, the weight comes as 3 newtons. So the answer is 3 newtons. Okay, guys, we're going to go ahead and we're going to stop it over here for today.